Today I'm going to present a tutorial about the core concept related to the reliability index beta. Why? Because I realize that many practicing engineer doesn't fully understand this concept that is central into the reliability of existing bridges. So, terminology. So there are two possible states of a system. Either it survives or it fails. Okay. Then when it fails, we talk about the states where the system doesn't fulfill its function. What does it mean? Either it's not safe or it's not apt for service. When we talk about reliability, we quantify it through its survival probability, where reliability is quantified by the complement of the failure probability. So PF is the failure probability, where F comes from failing. So if we want to look at this through an example, so let's see this bar that is subject to a tensile force S and that has a resistance R. Okay, so here if we look at the axis we have here in kilonewton, we can express the nominal resistance R as well as the nominal solicitation S. So we can see that in this case, the strength, or R, is greater than the solicitation, which means that everything is all right. But in practice, when we design such a member, okay, we want to make sure that no matter what happened, the strength is always greater than the resistance. So we're going to use coefficient that's going to reduce the strength and that's going to increase the solicitation. So in that case, if the weighted up strength is lower than the weighted down resistance, in that case, we're going to say everything is fine, no additional measure is required. However, what happens when this is not the case? So when this is a simple bar like this, okay, we can simply reduce the load or increase the capacity of our bar. But when this is a multi-million or multi-billion dollar structure, okay, what we want to do, we might want to go beyond this. Why? Because these factors, phi S and phi R, are usually code defined, and these values are meant to be applicable to all cases, no matter what are the specificities of our problem at hand. So in this case, it might be worth to do a more refined reliability analysis in order to see what is our really current state of knowledge about this exact structure. So in that case, what we need to do is not only use the nominal resistance, but to really use a probability distribution to describe what is our current knowledge about that resistance. And most often, the average resistance is above the nominal resistance. Why? Because the nominal resistance that we obtain from our calculation models is often the collection of several conservative hypotheses we've made in determining that resistance. This is the same thing for the solicitation. The mean solicitation is typically lower than the nominal one. So I'm pretty sure that if some of you have been taught about reliability, you've been taught about the intersection between these two curves. This is a common mistake because this doesn't represent the failure probability. Why? Because if we want to look at failure probability, we need to look at it into a multivariate domain. Okay, something like this. Both are the same thing, two different representations of the same thing. So in this case, we have this resistance, strength, R. This is represented by the blue curve here. We have the solicitation, the load, represented by the green curve here. So this square is the same as this one. So we can draw this line in both domain such that for all the points on this line, we have the same resistance and solicitation. Okay, so this is the frontier that separates the survival and failure domain. So everything in pink here or in pink here is all the possible cases for which the solicitation is greater than the resistance. So here what we need to add on this graph is what is going to be not only the marginal probability density, but the joint probability density, either represented through contours or through a surface, such that the probability content over the entire domain, so it means if I integrate under this surface over all possible values of S and R, I would obtain 1. If I want to compute my failure probability, so the probability that R lesser or equal to S, I need to integrate, but just over the domain that is in red here, that represents the failure domain. So in that case, that bidimensional integral would represent my failure probability. Okay, I went really quick through a lot of concepts. Before going there, we need to cover why should we want to use probability theory at first. Then, if we want to use probability theory, how do we use it? Using random variables. And in order to define random variables, core concepts are the expected value, variance, and correlation coefficient. We're going to go through them. And finally, what happens if we try to have the sum of random variables? So we're going to go through these 4 core concepts so that you can understand where does that reliability index come from. First thing, why would we want to use probability theory? Is it for describing random phenomena? Not necessarily, okay? Because most phenomena are intrinsically random. Take, for instance, this coin, okay? If we want to flip it to obtain head or tail, is it random? It's not really random, okay? We use it to represent not something that's intrinsically random, but something that represents our lack of knowledge. This is what we call epistemic uncertainty. Why a coin toss is not intrinsically random? Because we can simply generate a simple machine that will be able to make repeatable coin toss, okay, time after time, because it will repeat the same initial condition, the same speed, the same initial acceleration, okay? So it's not something that it's intrinsically random, it just represents a lack of knowledge, in this case about initial condition. So take the example of what is the Young's modulus at this location in a dam. Okay, locally, this Young's model doesn't vary. Okay, the only thing is that we don't know exactly what is its value. So why do we want to use probability theory? To describe our uncertainty or lack of knowledge about what is that specific value. So if we push that reasoning to the end, up to the reliability analysis, what it means that PF, or failure probability, is not going to be an intrinsic property of a structure. Okay, it's to be a reflection of our own knowledge about all the variables that enter into either the load or the resistance model that is used in computing that failure probability. Okay, so now if we want to look at random variable, okay, in terms of nomenclature, in terms of notation, we're going to say that capital X denotes a random variable. And this symbol means it's distributed following a probability density function. So that lowercase f of lowercase x is a probability density function, where the lowercase means one specific value for which the random variable can take. So capital X is the random variable, so it can take any value in the domain of x, and the relative plausibility of each of these values follows that probability density function. So here's an example of probability density function, PDF, for domain x, and just like the coin toss. So we know that the probability of each side is 0.5. So the sum of all possibility makes 1. It's the same for a PDF. Now, instead of being a sum, it's an integral. So if we make the integral of all the possibilities underneath this curve, we should absolutely get 1. So the key probability density function that we're going to use here for the reliability index is the normal PDF. So this is the equation for the normal PDF. We're not really interested in that specific equation. What we want to see is that there are 2 key parameters that we're interested in: the mean and standard deviation, or the square of it, the variance. So here's an example of such a normal PDF for a mean of 1 and standard deviation of 1. So you see that the top of that bell curve is centered on 1, and the standard deviation, measuring its spread, is of 1 as well. So in terms of intuitive understanding of these parameters, you can see the mean as like the center of gravity of this probability density function. The same thing as the center of gravity of a cross section for a member. The variance, you can see it as the measure of dispersion of that probability density function. So this is entirely analogous to the concept of inertia of a cross section. So center of gravity measures the centering position, the inertia represents the dispersion of the material. So the mean represents the center of a PDF, the variance represents its spread in the content of probability. Another representation of that PDF could be used through the cumulative density function, CDF. That represents the integral of my PDF from the lower bound until a value x that I want to try. Okay, so for instance, if I want to evaluate my CDF at 0, that represents the integral from the lowest point, minus infinity, up to 0. So basically, it's the area underneath my curve here, represented in blue here. And when I read the CDF at 0, it's like just going through my curve here and reading the value, in this case, 0.16. Okay, this is the definition of a CDF. we need to look at a special case, which is the standard normal random variable. Okay, the standard normal is the same PDF as the normal PDF, except that now I'm going to evaluate for mean of 0 and a standard deviation of 1. And we're going to typically denote it by a lowercase phi. So this is the same thing as before, but always the same parameter, mean 0, standard deviation 1. We have the CDF, and the CDF of a standard random normal variable is going to be denoted by a capital phi, okay? Lowercase phi, capital phi. Then we can draw here, it always looks at the same thing. So mean 0, standard deviation 1, we have the PDF, we have the CDF. And one thing we can always do is go from a normal variable to a standard normal variable. Okay, we want to go from any generic normal random variable x, mean mu, standard deviation sigma, to a 0, 1 standard normal variable. How do we do this? Through this transformation function. So we take our x random variable, we subtract its mean mu, we divide by the standard deviation, we're going to have our standard normal variable. Okay, this is always true, we can always do that. And so how does it look like to go from the generic normal random variable to a standard normal one? Okay, so if we have our generic random variable, in this case mean 1, standard deviation 1, we can evaluate, as we did before, the CDF at 0. That represents the area underneath the curve here in blue. This is like reading a CDF here. It's going to give us 0.16 like before. So now through this transformation function, we can say, I want to find a corresponding point in a standard normal variable. Okay, so x minus mu, 1, divided by standard deviation 1, that should give me my mu. So 0 minus 1 divided by 1, that gives me minus 1. I can evaluate this into my standard normal CDF at minus 1. This is what I obtained here. That's going to also give me 0.16. Okay, so we can always find a corresponding point x that corresponds to corresponding point u, so that the probability content here is always going to be the same. And we're going to need this later on to go from our reliability index beta through a probability of failure PF. We're going to come back to this. Before going there, we need to look at the bivariate normal random variable. So in this case, this is the expression for a bivariate normal random variable, where we have for x and y the analytical formulation. Again, we don't care about this specific analytical formulation. What we care about here is to see what are the parameters that govern those. We have 2 mean parameters, 2 standard deviation parameters, and a correlation coefficient. And if we look more closely at what is the effect of those, the first parameter here is I change the mean. So you see that if I change the mean for x1, it represents a translation about x1. If I change the mean about x2, it's a translation vertically about x2. Okay, so these are the measure of position of my density. If I change sigma 1, I'm going to change the dispersion about my first axis. If I change sigma 2, I'm going to change the dispersion about my second axis. If I change my correlation coefficient, I'm going to here increase I'm going to kind of squash my PDF so that I'm going to have a positive correlation that indicates that if I expect to have high values for x1, I should have a high probability of expecting high value for x2. If I put high negative correlation, what it means that if I expect high value for x1, I should expect with high probability low value for x2. Okay, this is the interpretation of those 5 parameters. Okay, and then before exploring a little more about the impact of this correlation coefficient, let's look at what happened when we sum random variables. Okay, let's imagine that we have 2 random variables, x and y, both having their own mean, their own variance parameter. So if we assume that x and y are statistically independent, represented by this symbol here, so we want to know what is the distribution of z that is obtained by the sum of x plus y. So in that case, we can find that z is also normal. And the mean of z is the sum of the mean of my 2 x and y's. And the variance of z is simply the sum of the variances. Okay, we can do this if x and y's are statistically independent. If they're not independent, such as their correlation coefficient is not 0, in that case, it's slightly modified my formulation. Z is still normal. Its mean, it's still the sum of the mean, but now its variance, in addition to be the sum of the variance, there's also another term that accounts for the possible dependency between those two variables. Let's put that into application to see what is the impact of our correlation coefficient. Okay, does it matter? It does. We're going to see it through this example. So let's imagine we want to compute what is the strength of a cable made of 50 individual wires, where the strength of each wire is modeled by a normal variable with a mean of 10 kilonewton, a standard deviation of 3 kilonewton. So in this case, we assume that the strength of the cable is represented by the sum of the strength of the individual wires. So in that case, if we make the assumption that each wire, its strength is independent from the other wires, the strength of the cable would be modeled by a normal random variable, which means 50 times 10, 500 kilonewtons, and with variance 21 kilonewtons, with standard deviation 21 kilonewtons. If we redo the same exercise, but changing the initial hypothesis, such that we assume that all the resistance of all of my wire are fully correlated, meaning that if one is high, all of them are high. If one is low, all of them are low. So in that case, the mean remains the same, but the standard deviation goes to 150. If we represent this visually, with the hypothesis that the resistance, the strength is independent, we have the red curve. If they are dependent, is the blue curve. From an engineering perspective, we by far prefer the red curve. Why? Because we eliminate all these low value probability for the strength of the cable. So we rather have the case where we're going to have independence between our different strengths, so that each wire, its strengths compensate the other, so that globally the variability in my resistance of my cable shrinks down. Okay, this is an example to illustrate how that dependency matters. Now we have all the elements to define and to establish what is our reliability index beta. Okay, and we're going to do this through what we call a margin of safety. We're going to call that margin of safety Z, and that represents the distance between our resistance R and our solicitation S. Okay, so Z is defined as R minus S. The greater Z, the better it is. If it goes negative, we're going to be in our failure domain. So we want to quantify our failure probability as a probability of the event where Z, my margin of safety, is lesser or equal to 0. And so I can evaluate this probability through the CDF, as we see before, the cumulative density function of Z evaluated at 0. So here what we need to do, if we want to evaluate that CDF, we first need to define its PDF according to its mean, mu Z, and standard deviation, sigma Z. So then we want to calculate this area underneath the curve that corresponds to a CDF evaluated at 0. So here, from the law of summation of random variable, we can compute mu Z being the difference between mu R and mu S. We can compute the variance of Z in the general case, like the summation of the respective variance minus the term to account for the possible dependency between R and S. So in that case, we saw earlier that we can go from that generic random normal variable into the standard normal one using that relationship. Okay, so now we want to evaluate the specific case where Z equals 0. So in that case, it corresponds to U equals minus mu Z divided by sigma Z. Okay, so in that case, we can represent not our Z space, but our U space, the standard normal one. So the probability content we're seeing here is absolutely equivalent to the probability content we're seeing here. Okay, so evaluate for a standard normal random variable, which has a mean 0, standard deviation 1, and we look at a distance of minus beta from the origin, where minus beta is what? Is minus mu Z over sigma Z. And that beta is our reliability index. So mu Z is what we obtain here. Sigma Z is the square root of the variance we can obtain here. So whenever you see in, for instance, bridge building codes, this formulation for the reliability index, this is exactly where it comes from. So if we want to obtain the probability of failure, we want to evaluate this integral here, we simply evaluate the standard normal CDF for a value of minus beta, this quantity here. And this is denoted, as we said before, by the capital phi. So we can express this relationship here expressed by this standard normal CDF between beta and the failure probability. So we can see that for typical structure, we're seeking a beta of around 3.5 that correspond to a probability of failure of 10 to the minus 4. So we're gonna finish this by applying it to an example. Let's imagine that the strength R has a mean of 20, a standard deviation of 5, the solicitation has a mean of 10, standard deviation of 5. Okay, or margin of safety is represented by R minus S. This is going to be normal. So if R and S are assumed to be statistically independent, mu Z is going to be 10, sigma Z is going to be 7. We calculated this with the expression we saw earlier. We can represent graphically what this PDF for Z looks like. So the failure probability is the area in red here. We can calculate it in the standard normal space by calculating our beta by the ratio of mu Z over sigma Z, these two quantities here, 1.41. So if we evaluate the CDF of a standard normal random variable at a distance minus 1.41 from the origin, the result is going to be PF, in this case, 0.08. And if we come back to what we saw earlier, that intersection between the two curves, in that case, this area represents 0.26. So we can see that this representation is not at all corresponding to that failure probability we've computed through the margin of safety. So is that all? Yes, it is all. Okay? This is all for defining and understanding the key concept behind the reliability index. Then why do we spend 45 hours teaching that topic at university level courses? It's because in practice, we neither know what is the PDF for R nor for S. So in that case, we need to define a limit state function, g of x, that in a simple case could be represented by the difference between the resistance model and the solicitation models, which both are a function of a set of random variables. These random variables can be associated with geometry, material property, boundary condition, etc. Okay? Then we need to define omega, which is going to be our failure domain. So all possible values of x, such as my limit state function, is lesser or equal to 0, meaning my failure domain. And then my failure probability is the evaluation of that integral, not over z, but this time over f of x, meaning this is the probability density function of all the variable that enters either in my resistance or solicitation model. And I made this integral over my domain omega. Practice, we don't like doing integral, and only we don't like it, we cannot solve analytically by and these integral. So the core topics in reliability theory is to find what could be either analytical approximate solutions or numerical solutions to evaluate these integral that are typically defined in very high dimensional domain. So if you want more information, so either videos presenting all the key concepts or the slides presenting the key concept about reliability theorem, you can go on my website. All the content for the full course are available there.